Hey, good afternoon, everyone. It's just after the hour, so I think we can get started. Happy New Year and welcome to the new seminars. If you didn't see the email yesterday, I just want to let everyone know about a few updates we have. Starting in February, we're going to be starting with some early career research presentations on the first Monday of every month. We'll have 2 speakers on the first Monday of every month. And then once a month, we're going to be trying to do a Python or a coding tutorial, introducing new coding and analysis routines relevant to space physics and magnetospheric physics to the community. So I hope everyone will be interested in those. For the other 2 Mondays in the month, we'll continue with our general 1-hour seminar review talks. So today, I'm delighted to have Jeffrey Love here from USGS, the US Geological Survey, and he's going to be talking today about the superstorm in 1989. Over his career, he has studied several aspects of geomagnetism. These days, he works in collaboration with colleagues in a general area of encompassing 3 subjects, using the geomagnetic monitoring data and magnetotelluric survey data to evaluate geoelectric hazards of concern to the electrical power grid for the industry, looking at statistical analysis of the rare occurrence of intense geomagnetic storms, and as well as analysis of historical records of past space weather events and their impacts. So we were happy to have Jeffrey talk about one of these a few months ago, and today he'll be talking about more recent geomagnetic activity and the 1989 storm. So Jeffrey, if you'd like to take it away.
Yeah, Kyle, thank you very much. Appreciate that. I'm happy to be presenting again today. Yeah, so I'm going to talk about the March 1989 storm. The subject of this presentation is actually a manuscript that we just submitted to Space Weather. And so happy to communicate the results. We're really going to talk about the storm, our retrospective estimation of geoelectric hazards that were realized across the contiguous United States during March 1989, and the impacts on the United States power grid as reported in publicly available sources. And I'll discuss some of that in a little bit of detail. This work, I just want to really emphasize, is very much a collaborative effort. I have my colleagues and I rely on them for things, and I like to think they rely on me for some things too, but for this analysis, they've made substantial and important contributions, including Anna Kelbert, Josh Rigler, Ben Murphy, who are all parts of the geomagnetism program at the USGS. Greg Lucas, who was a part of our program as a postdoc, but is now has a regular job at LASP at the University of Colorado, and Paul Bedrosian, who's a colleague at the USGS, who works in a different science center and provides important expertise on magnetotellurics. Just want to emphasize this work is motivated and is part of a coordinated federal government project known as SWARM, the Space Weather Operations Research and Mitigation. Oh, I see I misspelled mitigation, but Mitigation Working Group, which is part of the Office of Science and Technology Policy managed out of the White House. It's a very good project for coordinating work among different federal agencies on space weather, and I think it's been a great success. So here we have a beautiful picture. This is the eastern United States. Took me a little bit of time to recognize it at first. but I'll just kind of walk you through, and it really just nicely emphasizes how important electricity is for modern society. Up here is Boston. This is New York City, Long Island, Philadelphia, Baltimore, Washington, D.C., and Richmond, Virginia, and Norfolk, Virginia. It really is impressive how built up the Eastern United States is, and in some respects, how small the world is when you just understand how close in some respects these megalopolises are with respect to each other, given their geographic extent. Up here is, because I'll mention it, the impact on Canada. This is Montreal, and it's a nice picture also because it illustrates the aurora that is kind of looming over the horizon, which is, of course, one of the manifestations of magnetic storms. So with that, I will move to the next slide. So the March 1989 magnetic superstorm, the most intense storm recorded in the space age. So since IGY, maximum minus DST of 589 nanoteslas, if you use the Kyoto version of that, or 565 nanoteslas, if you use the Oulu version of that index, that is a big storm. Brought aurora and geomagnetic disturbance to mid-latitudes, including across the contiguous United States. And just want to advertise that storms of this intensity occur actually with some frequency. I have a recent analysis out which estimates that storms of this intensity occur on average about every 4 solar cycles. This storm disrupted satellite operations and damaged satellites, interfered with radio communication, navigation systems, and geophysical surveys. But it's most well known for the impact that it had on Quebec, causing a blackout in that province, which is an interesting subject. But today I'd like to discuss the impact that this storm had on the electric power grid of the United States. And it caused widespread interference, though not a widespread blackout. It damaged a high voltage transformer in New Jersey, for example, at a nuclear power plant. And, although it didn't cause a blackout, the interference in the kind of geographical temporal realization of that interference gives us some lessons as to where we might concentrate our efforts for future storms, which might very possibly be even more intense. Future storms such as intense as the Carrington event, or that of September 1909 or May 1921. So it's interesting and important to study this because the possible future occurrence of a magnetic superstorm could carry widespread deleterious impact to technological systems, especially for satellite systems and electricity power grid systems. All right, so I mentioned this already. This is a compilation I've been putting together of power grid anomalies for different magnetic storms. On the top here, we have a map showing where the power grid systems experienced some interference of various types during the March 1989 storm. Here we have in the center here the same thing, but for August 1972, and right here at the bottom for March 1940. This is not a complete list of anomalies that I put together. It's the anomalies that I could find, and it just so happens that they are mostly about these 3 particular storms. I have a list of anomalies for other storms as well, but the pattern is actually quite clear. There's a lot of interference occurring in the eastern United States, and interference tending to occur in the upper Midwest United States. So as I say, these anomalies are reported in publications. And for the March 1989 storm, there's a certain amount of detail, not as much as we might like. I'm working with what is available. The anomalies give their start times and have start times and end times listed. They're mostly at named facilities. I had to locate those facilities, which is really where some of the work was involved here. The severity of the anomalies are not really that detailed. but they include the Quebec blackout and damage to the transformer in New Jersey. And they're kind of qualitative. They just sometimes very brief description. There's an alarm that went off related to the magnetic storm, oscillograph, that's open to interpretation, capacitor, generator, voltage, MVAR, which is a measure of the inefficiency of a power grid system. But it is interesting to just look at these, qualitative though they might be, and realize that there is some geographic consistency, and that is telling us something important, I think. All right, so an important issue as to whether or not these anomalies are simply occurring in concentrations in the Northeast United States because we happen to have more power grid infrastructure there. So I also accessed a database of power grid substations and compared the distribution of those power grid substations to the distribution of the power grid anomalies, and compared the ratios of the two. And right here on the bottom, showing the density ratio of those two quantities, the anomalies and the density of substations. And we see that there is actually quite a substantial surplus of anomalies in the Northeast United States and the Northern Midwest, and a shortage or a smaller density of anomalies in the remainder part of the United States. So we can see from that we actually have a statistically interesting, and you might say significant, surplus of anomalies in those parts of the United States, which is something we're going to seek to explain here. So why are storms anomalies concentrated where they are and as a function of time? So why are they where they are and when they are? And conversely, why are they rare in other places of the United States is a question we're seeking to answer. And I'll just let you know the impact on the power grid system is essentially a conspiracy of three factors: the geographical temporal expression of geomagnetic disturbance, which is not homogeneous over the surface of the Earth. It has a geography and a time dependence. And that's important and something that space scientists are familiar with. There's also a geographical frequency dependence of the Earth's surface impedance. And this is where geology and the USGS becomes a relevant agency. The Earth is very heterogeneous in its composition, solid Earth is, and it has a heterogeneous electrical conductivity distribution. And that affects the surface impedance, that is the relationship between an inducing magnetic field and an induced geoelectric field. The impact is also a factor of power grid topology, the system components and the system parameters. And I'm not really so much going to be getting into that. I'm not an engineer, I'm a natural scientist. But it's important just to realize that this whole subject is a complicated function of multiple parameters, and that makes it interesting. And we'll be concentrating on the natural science and looking at the impacts. All right, so this is what I sometimes call my math slide. It describes, at least qualitatively, what we're doing. We have three different levels here of description, of increasing detail as you go down on the top, just in an abstract sense. If we have a filter, that filter can take a input signal and through convolution give you an output signal. That's just a straightforward time series analysis. In the case of the systems that we're interested in here today, geomagnetic variation driven by the sun interacts with the solid Earth, and this shows a geological cross-section, in this case of Virginia. And the interaction of that geomagnetic field with the solid Earth allows for the induction of a geoelectric field, and that is the quantity that is interesting for the power grid industry. So for this analysis, we're going to be putting together two different data sets, geomagnetic monitoring data, measurements made, in this case of the March 1989 magnetic storm, including at our observatory here in Fredericksburg, Virginia. That's a picture of our observatory. And we have several of them distributed across CONUS. And we're going to marry that magnetic data with Earth's measurements of Earth's surface impedance. And this is data that is acquired through surveys. Basically, you set up a magnetometer and you also insert a voltmeter into the ground to simultaneously measure geomagnetic field variation and geoelectric field variation. And it's a frequency band limited set of measurements over the frequency band of interest. You can work out a set of numbers that describe the relationship between magnetic field variation and the induced electric field. And those numbers are impedance. And it's a tensor. The tensor is a function of the solid earth conductivity structure. And for our purposes, that doesn't change over time. So once you've made enough measurements to work out those numbers describing impedance, you don't need to keep making the measurements. You take your measurement system, you pick it up and you move it to a new site and start over again. So it's a survey, it's not monitoring. So the marriage of those two data sets will allow us to work out a geoelectric hazard map. All right, so I just want to emphasize some of the data that are going in here, also emphasize some of the challenges that exist in this analysis. The data collected, geomagnetic data, monitoring data were collected in March 1989. For me, that was a while ago. I was still a graduate student. But we're using the data that we have to understand this particular storm. So on the left, we have a map showing the distribution of the monitoring stations that were in operation at that time across North America. And on the right, we have a stack plot showing the magnetometer data as, for I guess, 2.5 days of time, or 1.5 days of time, showing the magnetic field variation over this period of time that encapsulates the magnetic storm. So going from high latitude, this observatory here, PBQ, in northern Canada, Ottawa, and of course, just north of Conus, United States, Fredericksburg, Virginia, in Virginia, and the San Juan Observatory in Puerto Rico. See right away that there are some problems here. Unfortunately, and I apologize, even though it's not my fault, there was quite a big data gap in the San Juan time series during the magnetic storm, and there are some clipping of the data at the Fredericksburg Observatory. So we're conscious of this. Again, using what we have, but we're conscious of it. Turns out that this is actually not going to handicap us too much because we're mostly interested in describing geomagnetic field variation between Fredericksburg and Ottawa, and also not so interested in that particular period. It turns out when it was the data were clipped. So again, it's unfortunate, but that's the way the data are. Here we have the DST time series for this storm. There's a couple of sudden commencements that initiated the storm, the main phase of the storm, and then the really the most intense part of the storm maximum, you might call it, when the negative DST reached its maximum value. On the bottom here, just counting the anomalies in 1 hour bins that occurred across the contiguous United States, and we see that they occur in clusters, and in particular during the main phase of the storm and during its greatest depth. So we're going to concentrate in this discussion on these 3 periods of time when there were quite a few anomalies realized in the electric power grid across the United States during this storm. All right, so that's the magnetometer data and a little summary of some of the results of the anomalies. I want to emphasize here the surface impedance of the Earth and the measurements that have been made and which are useful for studying retrospectively the March 1989 storm. So on the left, we have some of the some guys working in the field, deploying magnetometers and those electric field measurements in order to make those magnetotelluric measurements that are used to calculate the surface impedance tensor. And on the right here, we have a graphical representation of the surface impedance across the contiguous United States. So we have quite a few survey sites, hundreds of them, perhaps even 1,000, that are going into this database or going into this analysis. Just want to emphasize, where the symbol here on the right is large, the impedance is high. Where the symbol is small, the impedance is low. Where the symbol is orange, the impedance is high. Where the symbol is blue, the impedance is low. And we can see right away that the impedance is quite different in different places. And on the bottom here, we have a scale showing the magnitude of the impedance. And in this case, it spans 3 or 4 orders of magnitude. Just think about that. In some places, the impedance is 100, as much as 1,000 times higher than it is at other places. In particular, it's high in the northern Midwest of the United States. And I want to emphasize that it's high along the eastern United States too. And the symbols, though, are shaped very differently in the eastern United States as compared to the Midwest. Here, the symbols are actually very needle-shaped. And that's telling you that the impedance is very polarizing. It takes a magnetic field and tends to create, allow for the induction of an electric field that is polarized in preferential directions. And that polarization happens to be from the southeast to the northwest. And that's related to the geology. There are kind of a horizontal stack of different geological structures, different tectonic structures here in the eastern United States. And their differences they have in terms of electrical conductivity means that the impedance tends to be polarizing there. Other places have low impedance, like here in Michigan, where geology is essentially sedimentary, and across much of the Western United States. It's quite complicated in the Western United States. There are places that have some high impedance, but for the most part, the impedance is quite a bit lower there than it is in the upper Midwest and then in the Eastern United States. So, all right, just want to emphasize that this heterogeneous impedance due to the heterogeneous conductivity structure is the a important factor in determining the hazard for the electric power grid industry. So if we just imagine that we have an electric current flowing in space over our heads, as represented by this red vector here, and that current is increasing in intensity, so it's time dependent. It then generates a magnetic field of increasing intensity, and that magnetic field interacts with that time-dependent magnetic field by Faraday's law generates an electric field in the solid earth, and the efficiency with which that electric field can drive currents depends on Ohm's law. So it depends on the conductivity of the solid earth. So through this induction, the electric fields are induced, and in pretty good conducting parts of the earth, that allows for a good flow of electric current. In parts of the earth which have relatively resistive, high impedance, the current doesn't flow so easily. Well, if you happen to have a power grid that's deployed across an electric resistive or high impedance geological structure, the current won't flow so easily through the structure, but can take a path of least resistance and flow through the power grid itself. So you end up having these uncontrolled quasi-direct currents flowing through a power grid system, which is of course designed for controlled currents, which are typically alternating currents. So that's the crux of the problem. Direct currents flowing through the power grid system can trip relays because those are unanticipated in a controlled operation, and they can heat transformers and cause damage to them. So there we are. That's the geological space weather connection to the impact on the power grid systems. Okay, so I mentioned that I'm going to talk in some detail, a little bit of detail about 3 different instances in time when we had lots of different anomalies across the contiguous United States. So one of the first steps in this analysis is that we take the magnetic monitoring data and we construct magnetic field maps, essentially interpolating it across the contiguous United States. We'd like to have more observatories, and hopefully in the future we will, but we have a limited number for this particular storm, but we're going to just push ahead and see what happens. So at these 3 different instances represented right here, we're showing the magnetic field and its perturbation over the course of the storm during these 3 instances in time. These are 2 instances of the main phase of the storm, showing different kinds of magnetic field variation. And then right here, this is the point at which the storm reaches its maximum intensity. These magnetic field instances are parts of a movie that we have showing the magnetic field variation over the course of this storm. And they can be represented in terms of an equivalent current system, ionospheric current systems, which we show down here, again, showing that at 3 different times during this magnetic storm, the current systems were very different and the magnetic fields that were being generated were very different. All right, so just walk you through now some of the results showing the geoelectric field amplitude induced across the United States and where we have survey sites, and show the estimated geoelectric field amplitude and then the corresponding realization of anomalies on the power grid system. So on the left here, at 10 o'clock through the end of the 10th hour on March 13th, the geoelectric field is a relatively modest amplitude, and we have no anomalies across the contiguous United States. The next hour, though, during the main phase, the geoelectric field amplitude picked up. We can see it right here. High amplitude in the eastern United States and some enhancement of amplitude up here in northern Minnesota. Because of geomagnetic disturbance and its geographic differences, but primarily because of different geographic differences in surface impedance, that geoelectric field amplitude differs substantially across the United States, from something like less than a fifth of a volt per kilometer to more than 20 volts per kilometer in the eastern United States. Then, even 20 kilometers or 20 volts per kilometer may or may not sound like a lot to you, but if you integrate 20 volts per kilometer across a power grid line that's, say, 100 kilometers long, you end up with a couple thousand volts, and a couple thousand volts DC, again, on the power grid system, which is designed for AC, is the crux of the problem. And sure enough, we see at this instant in time that the anomalies actually were realized. So we have a coincidence, not a random coincidence, but there's a causal connection here. When the geoelectric field is high in the eastern United States, we also have correspondingly power grid anomalies during this particular hour of the storm. So we see the same thing for the next hour, again, going from an hour of time before we had a lot of anomalies to an hour of time when we had a lot of anomalies. And again, showing enhancement of geoelectric amplitude in the eastern United States at the same time that we have more power grid anomalies. And then finally, at the most intense part of the storm, geoelectric field amplitude increases over this pair of hours. And sure enough, high geoelectric amplitude corresponds to the realization of power grid anomalies in the Northeast United States primarily, but also to some extent in the upper Midwest. So we're happy with this. We would like to have more detailed power grid anomaly data, but this does show us that we're on the right track for constructing these geoelectric hazard maps, because power grid anomalies occur when and they occur where the geoelectric field happens to be of high amplitude. We also understand that that is related to areas of the contiguous United States that tend to have high surface impedance. Okay, just to emphasize that, in this plot, we integrate all the results over time, showing the maximum geoelectric amplitude here on the left as realized over the course of the March 1989 storm, and the integration of all the power grid anomalies realized over the course of this storm. And here again, see their concentrations in the Northeast United States, the Mid-Atlantic through the Northeast United States, which is, as I've already emphasized, where the United States has some of its largest and strategically most important cities. Okay. So another thing I want to just emphasize here is the organization of the geoelectric hazards that is brought about by surface impedance. And here I'm plotting the maximum geoelectric amplitude realized over the course of this storm on the vertical axis versus transfer function amplitude, that is the impedance amplitude. And we see that the maximum geoelectric amplitude is organized in terms of where the surface impedance is high. We have this kind of power law relationship between those two quantities. So that emphasizes the importance of surface impedance for making maps of the storm-induced geoelectric fields. And it shows that that organization occurs across orders of magnitude. All right. So you might be wondering, well, what about the auroral electrojets? Those climb down from northern latitudes, sweep across CONUS latitudes during the magnetic storm. How do they relate to this organization of geoelectric hazards? Well, if we divide this data set into two parts, the two proximally equal parts, those with latitudes less than 50 degrees north geomagnetic, and those with latitudes higher than north geomagnetic, we see that there is an organization which is related to the structure of the auroral electrojet. The difference between these two subsets of the data is about a factor of 2. So the manifestation of the auroral electrojets, which are of course the source of the magnetic storm, their geography is important, but it only adds about a factor of 2 to the geographic variance in the geoelectric field that's realized during the storm, whereas surface impedance adds about 2 or 3 orders of magnitude. All right, so this work is also consistent with other work that we've done. We've taken the electric amplitudes and we've projected them onto the power grid geometry of the United States, showing where, and then integrated them across the power grid lines to estimate the voltages that are actually experienced on lines across the contiguous United States during intense storms. And this is a hazard map showing what that maximum voltage would be expected to be on a once per 100 year storm. And it ranges from about 1,000 volts to something quite a bit less than, or quite small, something just a few volts. So this is work that I'm actually quite proud that our group was able to put together. It was led by Greg Lucas, co-author on this presentation, but he led this work in putting together this hazard map, and it got us some good press from IEEE Spectrum, from Energy Wire, from National Geographic, Scientific American, and spaceweather.com, Bloomberg News, etc. So it's, the public is interested in this kind of product, which really just shows things visually, is something that I think that they can appreciate. So another project that we're working on in collaboration with NOAA is to put together time-dependent geoelectric field maps for the contiguous United States in real time. So these time-dependent maps in real time. And that's an ongoing project, which I think will, as we continue to make progress on it, be a very useful product for the power grid industry. All right, so I'll just wrap up with my conclusions. Mapping the geoelectromagnetic fields across CONUS during the March 1989 storm presents challenges that are related to the sparsity of observatories. There's only so much data, the quality of those data collected in March 1989, and the incompleteness of surveys. And I forgot to mention, in some of these maps I've shown of surface impedance and geoelectric amplitudes, the southern sector of the United States is not complete. But we're working to complete that now. Congress has appropriated money to the USGS, and we have a working relationship with Oregon State University to complete that survey across the southern sector of the contiguous United States. During the March 1989 storm, power grid interference was concentrated where surface impedance is high, and when and where geoelectric amplitudes were high. This observation serves as partial validation of our geoelectric mapping project. And just emphasize again, the geoelectric hazards tend to be high in the northern Midwest, the mid-Atlantic, and Northeast United States. Grid systems can be affected by during different phases of a magnetic storm at different local times and by a variety of ionospheric currents. So I say that because scientists in their efforts to kind of reduce things to the simplest model for purposes of explanation sometimes try to find the ionospheric current system that's the most hazardous for the power grid industry. And that's fine, but I would just say during a intense magnetic superstorm, there's plenty of geomagnetic activity to go around during multiple storm phases, and you're not going to isolate one particular current system as being particularly hazardous for the power grid. Geoelectric hazards across CONUS are primarily organized by surface impedance. There's a weaker organization due to the latitude dependence of auroral electrojets, and that's detectable. Having said that, there wouldn't be any geoelectric field induction if there wasn't a magnetic storm. So there is definitely a overall control of the amplitude of the geoelectric hazards due to the magnetic storms, but the geographic organization is primarily due to heterogeneous Earth conductivity. This work demonstrates that we need a denser network of magnetic monitoring stations across North America. We need to complete the magnetotelluric survey, including across Canada, which would be a very interesting project, and the importance of completing the national survey across the contiguous United States. And much work remains to be done to integrate studies of natural geoelectric hazards with studies of power grid vulnerability so that proper mitigation can be performed and the grid's made resilient. All right, so with that, I thank you for listening in on my presentation. I'm happy to take any questions that you might have.
All right, thank you, Jeffrey. That was a great talk. And we do have a handful of questions that I'll go through, and I'll just read them out for you. The first comes from Lynn Wilson. As for power grid anomalies, is there a reluctance in industry to admit that issues have occurred, i.e. like insurance coverage issues, if they do admit an anomaly occurred resulting from space weather?
Yeah, that's a great question, and I'm not going to point fingers at the industry, but I'll just say that it's not really part of their culture to be announcing publicly when they have this or that problem, unless, of course, it has a dramatic impact on the communities they serve. So yeah, they have lots of issues that they're always having to deal with, everything from wildfires to ice buildup on their power grid lines and magnetic storms. And sure, it would be great if there was more transparency and openness and exchange of information about the interference that's brought to power grid systems by magnetic storms. The Federal Energy Regulatory Commission, FERC, has mandated that the power grid industry start collecting GIC data, geomagnetically induced current data, and making those publicly available. So there will be some more transparency on the subject in the future. But I would just say that it's just hasn't been part of the culture to advertise that kind of information.
Excellent, or great answer. Our next one comes from Riley Troyer. Do you have any data from the smaller grid in Alaska, either for specific storms or just generically for geomagnetic hazards?
Right, so I don't have any anomaly data for the power grid systems in Alaska. That would be really interesting. We can at least conceivably calculate the geoelectric hazards. So the hazards are different than the impact, of course. And there is some interest in performing the magnetotelluric surveys like we have for CONUS across Alaska. There is some measurements have already been made, but a kind of systematic statewide survey has not yet been accomplished. That would be very interesting, but it's not yet yet realized.
So the next question comes from John Hidusik. When he explains space weather to lay people, he's sometimes asked whether we can extract useful energy from the magnetic field variations induced during geomagnetic storms. Are you aware of any attempts to do this?
Yeah, I get asked this question occasionally. I'm not aware of any specific attempts. I can imagine that something might be possible. I don't know how efficient it would be. As soon as you have voltages induced on a power grid line, you get currents being driven through those lines. It's not controlled currents. That would make it something of a challenge for harnessing. So I don't know the engineering, but I can just imagine it would be a challenge. And of course, really intense storms that create really big voltages that might be what are most useful for capturing power don't occur that often. So I don't know about the particulars and how practical that would be.
Yeah. So Eric Lund asks, have you any sense of how these hazards would affect or might apply to electrified railways, like the Amtrak Northeast Corridor?
Yeah. I'm sure that there are challenges for electrified railways in the Northeast United States during magnetic storms, but I don't know the details of what those problems really were manifest, say, during the March 1989. I don't have any records of that. Those kind of long line conductor challenges that the power grid industry has and are shared with the railway industry and also the pipeline industry. And it's a little bit different. The grounding is completely different. I don't know how susceptible those operations are to a magnetic storm. I'm most familiar with the power grid systems, but it's something worth continuing to look into. There's also another issue about transoceanic telecommunication cables lines. Those also have some vulnerability to magnetic storms, but again, I don't know the details of that.
So Howard Singer has his hand up, and just in case it's
okay.
with regard to one of the last two questions, I'll just ask him to unmute and comment.
Well, thank you. First of all, great talk, Jeff, as usual. But I wanted to go back to the question that was asked about harnessing the energy.
Oh, yes.
And there's one answer I always give, and that is in 1859 event, the telegraph operators cut off the batteries
Yes.
from their operations and powered the telegraph by the auroral currents, they say.
That's right.
So that is one example of maybe not what was being looked for, but it is an example.
That's right, and that's an interesting example, Howard. And thank you for bringing that up. In that case, all they had to do was open and close the circuit line, which is what a telegraph system basically does. So you get current, you don't have current, you get current, you don't have current, depending on whether or not it's open or closed. And the natural current that was being induced was sufficient to transmit that signal. So yeah, Howard, that's a great example. I appreciate your bringing that up. So
our next question is from Richard Glassner. Was there any seismic anomalies during the '89 superstorm?
I get this question fairly often. Can space weather cause earthquakes? Maybe that's what this question's about. And I would say the short answer is no. There's no demonstrable connection. Having said that, I emphasize that everything is related to everything else. So there's always bound to be some connection of sorts, but the size of the connection, the cause and effect relation between space weather and magnetic storms, or space weather and earthquakes, is just so small that it's just utterly undetectable. There are earthquakes occurring all the time anyway. They would occur with or without magnetic storms. So,
So we have a question from YouTube from Chris Davis today. Are there any significant differences across the US in how well protected different regions of the power grid are from these sort of anomalies?
I don't know the answer to that. That's really getting into the details of power grid operations. I will say that that power grid companies take space weather very seriously, and when they do get an alert from NOAA that a magnetic storm is on its way, they do put their operators on notice, and they are prepared to reroute electric transmission along different lines. They bring on additional levels of generating capacity to give them operational flexibility. But whether or not one particular grid system, part of the grid system, is more prepared than another, I can't tell you that. I don't know.
Similar question, not sure if it was a follow-up from Bert Vanderord. Could industry apply grid topologies that would make the grid less vulnerable?
Yeah, that's a great question. And so we have a couple of different products that we put together to help with that. So we project the, I'm going to try and see, can I back up here? We do project the geoelectric hazards onto the existing power grid system to give them an understanding of where their existing lines have hazards. But we also show geoelectric hazards more abstractly in terms of just the geoelectric amplitude across the contiguous United States. So these kinds of maps really do show where the power grid industry needs to concentrate their efforts, and if they want to put in additional power grid lines, where they need to make those lines more resilient. I will also say that this issue, which I briefly brought up here, of the polarization of the geoelectric field across the eastern United States, I think is an interesting one. And what that means is that if you were to deploy a power grid line across the Appalachians, it's more exposed to geoelectric hazards than a power grid line that is deployed along the length of the Appalachians. And so that's useful, and I think geologically interesting information that the power grid industry can use for being smart about developing their future smart power grid lines. So yes.
Excellent. So I have one question. You mentioned that this work was submitted. Is it available for preprint yet, or is it on a preprint server if anyone wants to access it?
It isn't, and I apologize for that. That's kind of a USGS regulation. This kind of work has policy implications, and before it is fully distributed in print form, it does need to go through a review process that is a USGS internal review in addition to the journal review. I will say that as soon as it's out, I will be happy to post it. I will post it on LinkedIn, and it'll be out there. But this kind of issue has been discussed in a lot of detail with some publications that are already out there. So, for example, this result here, this is a result from a couple of years ago, and that is published, and the reference is right there at the bottom.
Excellent. Yeah, and so those references will be available for everyone on YouTube too.
Oh yeah.
But thank you, Jeffrey. Oh, sorry, one more question came up. Is it possible to have a transmission line with adjustable impedance that could mitigate the hazards?
Well, that's interesting. The impedance that is important here is the impedance of the solid earth, and there's no way for us to adjust that. What can be adjusted is where the grounding connections of the power grid are with respect to the solid earth. And there are some projects to essentially install capacitors at some of those grounding connections to prevent GICs, geomagnetically induced currents, coming from the ground into the power grid lines. The difficulty there, though, is that there's a lot of grounding connections. There's hundreds of thousands of them, if not more. And to kind of shut the current off at one particular point in the power grid system just means that the current will flow in a different way through the power grid system. So just shutting off at a few points won't help that much. Well, it might help, but it is the dynamic reaction of the power grid system is something that really just needs to be understood. So.
All right, well, thank you, Jeffrey. This was an excellent talk. We have a few compliments, so I just want to echo them. Great talk. Thank you for presenting. Our next talk is going to be January 24th, after the holiday Monday, and Denny Oliveira will be talking about satellite orbital drag in low Earth orbit. So thanks again, Jeffrey, and I hope that everyone has a wonderful week.
Thank you very much. Thanks for tuning in.